Hey there! In this video, we're going to look at some differential equations applications, in particular, population models. Now, whenever we're talking about modeling in math, we're trying to come up with equations that describe real-world situations. So with population models, we're looking for equations that will describe the growth of some kind of population. Now, that can be a population of people or animals or viruses. Lots of different things can be described using a population model, whether they're growing or decaying. So the first type of population growth model that we're going to look at is an exponential growth model. Now this should be kind of familiar to you, although this differential equation itself might not be. So when we're talking about a population that's growing, that is proportional to the rate of growth is proportional to the population, then that's a differential equation that looks like this. So here I have dp dt equals k times p, where k is some constant of proportionality or growth constant, and p is your population, t is the time here. And if I know what the initial population is, that would be my P naught. That is the population at time zero whenever I choose that time zero to be. Now, I'm not going to solve this differential equation in this video, but I am going to give you the equation that you will get from solving it. So if I were to solve this, plug in those initial conditions, I would get this formula here. And just a note on the constant of proportionality, if it's positive, then we know that the population is increasing. If k ends up being negative, then the population is decreasing or decaying. So the solution to this differential equation is P of t equals P naught times e to the kt. So this is the formula that should be somewhat familiar to you. You may have run into it in a previous math or science class. Now this is a great population model, but it does have some drawbacks to it. The model is assuming that birth and death rates are constant, which is not always going to be the case. And it's not very accurate over a large population or over a really long period of time, because it's just not really taking in a lot into account. For instance, limited space or resources not being taken into account with this model. So for a long-term or really large population, it's not necessarily the best model to use. If we want to take some more factors into account, then we can use a logistic population model. So this is an example of a logistic equation. You might see some variations on this, even in our homework, you might see some variations. But this one has a proportional, the rate of the population, the change in population is equal to that same growth constant k times p times the quantity m minus p. Now here, M is going to be the carrying capacity for the population. This is also, you could also call this the maximum population for that for environment can sustain over a long-term period. It's also sometimes referred to as a limiting population. Right? So this usually has to be given, or we need enough information to actually find it. Now, again, this is a differential equation that we would be able to solve. It is separable, so I could use separation of variables to solve it. I'm just going to give you for this video, though, what that solution would look like. And depending on what resources you're looking at, you might see some variations of it, but it should look pretty similar to this. If I'm using that initial condition that the population at time zero is P naught, then we get P of t equals M divided by 1 plus the quantity M over P naught minus 1 times e to the negative kt. So we need a little more information for this one, but it is going to be a little bit more accurate than that exponential one for larger populations or longer periods of time. So this model also does not account for everything. So keep in mind, it does have its limitations as well. It doesn't account for immigration. So maybe population coming in from a different area, immigration, population exiting the area, or environmental factors such as limited space or resources. Now, we're going to do an example with this one, though, just so we can get comfortable with using it and finding the equation in a given situation. So, for our example, for part A, we've got in 1980, the population of alligators on the Kennedy Space Center grounds was estimated to be 1,500. And in 2006, the population had grown to an estimated 6,000. For part A, we want to estimate the alligator population at the Space Center in the year 2020 if the population grows exponentially. Okay, so they said it grows exponentially, so I'm going to use the exponential formula for this first one. I'm going to start by pulling out some of the information they gave me and translating it into some math. So the 1500 is my starting population. We're going to say 1980 is time 0. So P of 0 equals 1500. 2006, well, that's going to be 26 years later. So P of 26 would be 6,000 here. And I'm going to use that exponential growth formula. P of t equals P naught times e to the kt. So they've given me P naught. That's going to be the 1500. I can plug that into the equation, and I now have 1500 e to the kt. I don't have k, though. And that's why they gave me that second piece of information about the population in 2006. It's going to allow me to substitute into this equation and solve for the growth constant k. So that's exactly what I'm going to do here. I'll plug in the 6,000 for P of t and 26 for t. And then I'm going to solve this equation to find k. So to solve this, I'm going to divide by 1500. So 6,000 divided by 1500 gives me 4 on the left side is equal to e to the 26k. And then to get rid of that e on the right side and get the 26k out of the exponent, I'm going to take the natural log of both sides of this equation. So I'll get the natural log of 4 on the left, and the natural log of e to the 26k simplifies to just 26k. All right, so we're almost there. Dividing by 26 will find me my k value, which I am going to approximate. So the natural log of 4 divided by 26 gives me about 0.0533. Going out about 4 decimal places is pretty standard here. So we're being really exact with our answer. If you wanted to be super exact, you'd use the natural log of 4 over 26. But the decimal is usually going to be good enough. Okay, so I found k, which means I have my full formula now. P of t equals 1500 e to the 0.0533t. And now I can use it to answer this question, which was to estimate the population in 2020. So 2020 is 40 years after our starting time of 1980. So I'm looking for P of 40. And I'm going to plug 40 in, and I get 12,648 alligators as the estimated population after 40 years. All right, so now let's do this using a logistic formula instead. So I have the same initial conditions, P naught equals 1500, and in 2006, we're still going to say the population is 6,000. And now I have this additional information that the carrying capacity is 9,000. So that 12,000 that we just got in part A is looking a little less realistic now that I know the carrying capacity for this area is 9,000. So I'm going to switch up formulas, use the logistic formula, and I'm going to plug in the P naught to give me 9,000 over 1 plus 9,000 divided by 1,500 minus 1 times e to the kt. Now that 9,000 over 1,500 minus 1, I can simplify that down to 5. And I get a little bit neater equation here. So 9,000 divided by 1 plus 5 e to the kt, negative kt, is my equation. I still don't have that growth constant k, though. So I'm going to use the P of 26 equals 6,000 once again to find k. So different equation. I need to use slightly different steps here to solve this equation. I have a fraction on the right side, so I'm going to multiply both sides of this equation by that denominator. So I get the 6,000 times 1 plus 5 e to the negative 26k is equal to 9,000. And then I can start solving it, which I distributed the 6,000, not necessary really to do that. You could just have divided by the 6,000 if you wanted to. Here now, I'm going to subtract 6,000 from both sides. So 30,000 e to the negative 26k equals 3,000, and then divide by 30,000. So I end up with 1/10 on the right side, and that's equal to the e to the negative 26k. And so just like the last equation that we solved, I'm going to take the natural log of both sides to get that negative 26k out of the exponent. And I did do a little bit of simplification using some log properties here because I had natural log of 1/10, which can be simplified to negative natural log of just 10. It just cleans up the answer. It's not a necessary thing to do, but I'm using the exponent rule for logarithms here. 1/10 is the same thing as 10 to the negative 1. And then that exponent I can pull out front of the natural log to get a negative natural log of 10. Okay, so you don't have to do that, but if you want to, or you see it in a textbook or something like that, that's what they're doing. So last step now, divide by that negative 26 to get k. So I end up with a natural log of 10 divided by 26, which is approximately 0.0886 for my growth constant. So once again, I have my equation. P of t is now equal to 9,000 divided by 1 plus 5e to the negative 0.0886t. And finally, I can answer their question, which was, again, what is the population estimate in 2020? So I'm going to plug in P of 40 again to this equation. And this time I get only about 7,864 alligators. So definitely a smaller population when using the logistic model where we're including that carrying capacity.